You're not saving this.
Okay, let's go ahead and get started. We're going to talk about conductors today. Okay. Welcome back. I looked through the talk that President Oaks gave on Tuesday, looking for some quote that I could use this morning. And there's so much in there. There's just so much beautiful doctrine. But I settled on this quote. We need one another's prayers. I feel the positive effect of your prayers. I'm thankful and I love you. And I chose that because I feel the same way about you. Okay, I'm grateful for your prayers before we start each class. And I'm thankful for you and I love you. And you're wonderful people and it's not your fault. It's your parents' fault. Raised you right. Would someone be willing to give us an opening prayer today?
Our dear kind Heavenly Father, we are very grateful for the chance that we have to be gathered here this morning. We are very grateful for this beautiful campus and for the opportunity that we have to learn by both study and by faith, that we have professors that value that. We're grateful for the opportunity that we have to learn physics this morning from Dr. Francis. We ask you to bless him in his teaching and in all of his endeavors and bless us, that we may accomplish our goals and that we may be guided by the Spirit in doing so. We love thee, Father, and we say these things in the name of thy beloved Son, Jesus Christ. Amen.
Well, this morning when I was putting this on, I couldn't figure out why they had this extra buttonhole here, but now I figured it out. So, before we talk about conductors, we need to talk about this idea of symmetry. And symmetry is one of the most powerful tools in physics. And basically it's this. If the problem looks the same when I stand on my head as when I stand upright, then the answer must look the same when I stand on my head as when I stand upright. If the problem looks the same if I rotate my head by 30 degrees, the answer must look the same if I rotate my head by 30 degrees. And in this part of the class, when I say problem, I mean charge, the excess electrons or lack of electrons. If that charge has a spherical symmetry, if it's in a ball, then the answer, by which I mean the electric field created by the charge, must have spherical symmetry. And that's what we found last day. If I had a ball of charge and it was positive, I had field lines that were radially outward, evenly spaced. If I turn my head by 30 degrees, the ball of charge looks the same and the electric fields look the same. They have the same symmetry. I like this cartoon, this far side. One day, Wilson, I'll be sitting at that desk. And the reason we laugh is because you can't tell the left desk from the right desk. And that's another form of symmetry. If the problem looks the same when I look at it in a mirror, then the answer has to look the same when I look at it in a mirror. And we're going to see that in this fourth tutorial. I found this on the internet. It says, zur falschen Zeit am falschen Ort im falschen Job. at the wrong time, in the wrong place, in the wrong job. Yeah. Okay. So what we learned last day, just really quick, some of you weren't here. I assume that you watched it online, but we can use those field lines to paint a picture of the electric field everywhere in the room. And where the electric field lines are close together, I have a big electric field. It's stinky there. We talked about lines of stink with Pepe Le Pew. And the same thing's true with electric field lines. When they're close together, lots of electric field. And the direction of that electric field is tangent to the field line. Well, it's not on a field line, so I have to find the direction tangent to this field line and the direction tangent to that field line, and then just average between them. We call that interpolation. Now, at this point here, they're further apart, so I have a weaker electric field. And then over here, they're really far apart, so I have a very weak electric field. And it makes no difference at all that that point is on a field line. That just makes it easier to figure out the direction, but it's the distance between the field lines that determines the strength, not how close you are to a field line. Okay? See if your neighbor remembers all of that from the class they didn't come to.
Our interaction with laws is the way, like out there. On the line. Yeah.
Okay. Up until now, all of our charges have been either point charges or spherical charges. They've been concentrated. Well, now we're going to look at a different, very, very important distribution of charge, and that's a sheet of charge. Now I'm constrained to write, to put my lecture slides on this flat piece of screen. But if you use your imagination and see this green line as a sheet of charge that comes right out into the class, some of you are above it, some of you are below it, you got cut in half, okay? And it comes out forever, okay? And we characterize this sheet of charge with the Greek symbol sigma, a Greek S. And that stands for the surface charge density, okay? And what it means is if I had a 1 meter by 1 meter chunk of that sheet, how many coulombs would be in that 1 meter by 1 meter? So the units of sigma, as you can imagine, it makes sense. The units would be coulombs per meter squared. And the per we pronounce as for each meter squared. So if I had charge paint and I painted this tabletop, I would want to, if I want a uniform sigma, I would want to be careful to paint with the same thickness of paint everywhere on the table. Does that make sense? Do you see what that sigma is? It's how much charge I have in a unit of area. Now, the question is, what does the electric field look like due to that? Sir, what's your name? Joe. Joe. Thank you. That's so easy. Oh man, I can do that. Okay, Joe. Let's say that this table is really, really big. Okay, it just goes on forever, and you're on one side and I'm on the other. I can barely see you. Is it, hey, Joe, you still there? Yes, you're way out there. Okay. Now we paint this table carefully with charge paint that's positive. Okay, and I get the same thickness everywhere, and I I say, Joe. Get a straight one. Yeah. I bought these at Home Depot. I look like a real fool trying to figure out which ones were straight. So this represents a field line. And Joe, I'm telling you, I think the field line right here goes like that. How do you feel about that? Does that seem reasonable?
I feel like it wouldn't.
Oh, you feel like it wouldn't. Okay. So Joe's questioning my ability to find field lines. And that's a good thing. Okay. Because Joe and I see the same problem. I look out in front of me. I see what looks like an infinite flat sheet of charge, goes on forever. Joe looks out in front of him. He sees the same thing. Big old sheet of charge going out forever. If we both see the same problem, the same charge, we should see the same answer, the electric field, which is represented by the electric field line. I see a field line that goes up and to the right. What do you see, Joe?
Up and to the left.
Oh, I see up and to the right. He sees up and to the left. One of us is clearly wrong. Or this is wrong. And this has to be wrong. It has to have the same symmetry. And that means that the only reasonable symmetry would be perpendicular. Okay. Now, I say that the next one here looks like that. And then the next one here looks like that. Joe, how do you feel about that?
Good.
Okay. Now, I see them getting further apart as we go to the left. What do you see, Joe?
Closer together.
Okay, as they go to the left, they get closer together. I see as I go to the left, they get further apart. We see the same problem, the same sheet of charge, but we don't see the same answer. And so that means I can't have a spacing like this. They have to be evenly spaced so that Joe and I see the same solution, the same field lines. I look and I see perpendicular field lines that are evenly spaced, and so does Joe. Okay, so there's the first one, and then we just put the others. Now, indeed, this goes out in all directions, and so it should be field lines that are evenly spaced in all directions, and I've done my best to make that happen. You better be straight. Aha. Okay. Anyway, you don't want to wait here and see me play with Tinker Toys. But these would be the field lines. Okay. Now, one more. Now, if I look from this direction, they're evenly spaced. If I look from this direction, they're evenly spaced. Joe sees them evenly spaced. Okay. Now, the question is, and again, whether Joe and I look at the top of the sheet or the bottom of the sheet, the problem looks the same. And so we can argue that there must be field lines going down out of the bottom of the sheet as well that are evenly spaced and perpendicular to the sheet. Okay. Now, that's for an infinite sheet of charge. And we don't have infinite sheets. Typically, we've got a sheet that's finite in its dimensions. And so if we look at the electric field lines due to that, we find that they curve, they bend away, indicating that the further away I get from that sheet, the weaker the field. Now, it turns out that a whole lot of physics happens really, really close to the surface of objects. We call it surface science. And so a lot of physics happens right down there, right next to where the charge is. And so if you are close to the charge, compared to what? Well, compared to the edge of the sheet. So that when you're down here, you look out and it looks like an infinite sheet of charge. In that case, if I blow that up, it looks like that. And we call that the infinite sheet or infinite plate approximation. And that is actually very good approximation for a lot of physics that goes on. A lot of physics that goes on. Well, again, how close do I have to be to that sheet for this approximation to work? I like this cartoon again from the far side. Face it, Greg, you're lost. You know, if you're so close that it looks the same in all directions, then you're close enough. You're close enough. Close enough to the plate that all directions look alike. Now, I have a very important question for you. You remember what the electric field is. It's the blue vector, right? And it has those waffle words. If I reach into my pocket, and if I pull out +1 coulomb, and if I put that +1 coulomb at the X, how would it be pushed? That's what the electric field is, okay? And so if I tell you that if I reach into my pocket and if I pull out a +1 coulomb, and if I put it there, it would feel 5 newtons. Then the electric field at that location would be 5 newtons per coulomb or for each coulomb. Now, my question to you is, if the electric field is 5 newtons for each coulomb there, what about that other X, the one at the higher point? Is that going to be larger, the same, or smaller? With your clicker, and I've
Reading and
put this in the wrong place. Okay, now you can click.
It is further away from the charge.
That'd probably be like the same.
Oh, it's the. I don't know.
It's like.
Okay, last call. Get your vote in. Whoa, okay. Let's see what we said here. $137 of us said the same, and 82 of us said smaller, and that's the person you invite to your party. That one right there. Okay. Now, people, we don't agree here. We don't agree. And the reason we don't agree is because we've fallen into two camps that I call the believers and the unbelievers. Okay. We have some unbelievers among us, people. Okay, believers in what? Well, believers in field lines. Okay, if you believe in field lines, and if these field lines are parallel to each other, okay, I have the same spacing between the field lines here as I do up there. And that means that the electric field up there has to be exactly the same. Exactly the same. So the answer is B. Okay. Find out if your neighbor's a believer or unbeliever.
Or like the G.
Same distance, so they have.
It
doesn't matter where it is.
But I guess for me,
That just applies for point charts. That formula. Yeah.
No, that's fine.
Okay.
But nothing else.
Okay. So some of us are struggling right now and saying, whoa, how can that be so, Greg? That just does not seem intuitive. We've been saying that the electric field strength depends very strongly with distance. 1/r squared. We've been saying twice as far away is 1/4 as strong. And now all of a sudden you're saying, oh, distance doesn't matter. Nah, it doesn't matter. Okay. And the only thing I gave you to say that's true is symmetry. That's all the argument I gave. So let me try to justify that. And I'm going to do it 3 ways. I'm going to take 3 kicks at this can. But before we do, this is a scripture in D&C 88:33, one of my favorites. For what doth it profit a man if a gift is bestowed upon him, and he receive not the gift? Behold, he rejoices not in that which is given unto him, neither rejoices in him who is the giver of the gift. The gifts are those field lines. Okay? Those unbelievers in the room just threw those away and say, oh, well, I got charge there. This one's closer than that one. That must be a stronger electric field. Okay? Don't throw away the gift on the exam. Okay? If I went to all the trouble to make field lines for you on the exam, be happy. That's going to be the easiest question on the exam. Don't throw away the field lines. Use them. Okay? Now, let me take the first kick at this can. If I were to have a wall there and you saw those field lines, okay? Do you know what's making them? I mean, it could be a positive sheet of charge down here. Couldn't it also be a negative sheet of charge up there? Okay. And if that was a negative sheet of charge up there, wouldn't these field lines also need to be going towards a negative? I'd need field lines going towards the negative, field lines going towards the negative. Those field lines could be created by either of those sheets, either the positive sheet down here or the negative sheet up there. If distance mattered, you would want this to be the stronger electric field, whereas before you wanted it to be the weaker electric field, right? Talk to your neighbor, see if that convinces them. I still got 2 kicks at this can.
Still the same in that.
You answered it.
Okay.
So all the lines.
The answer is the same.
Like, it doesn't. still-
What we find is that near a plate or a sheet of charge, the electric field is independent of the distance from the sheet. Independent. All it depends on is how thickly I spread the charge. Remember what that sigma is. It's how many coulombs I have in 1 meter squared of area. Now, what's that nasty thing? That's called the permittivity of free space. And it has a value, 8.85 times 10 to the minus 12 coulomb squared over Newton meter squared. And that is one of the most important constants of the universe. It turns out that that is related to the speed of light, and it just keeps coming back over and over again. Now, remember, when we were dealing with point sources, point charges that were creating electric field, the distance mattered a whole lot, 1 over r squared. And here the K is that 9 times 10 to the 9th Newton meter squared over Coulomb squared. And so what we see is that now we've got 2 formulas for the electric field. Okay? We used to just have Coulomb's law, but now we have a formula that works whenever we have a big old sheet of charge. And it doesn't matter how we get our electric field, we can still use our operational definition of the electric field. The force is equal to the test charge times E. That's the F equals MA for this part of the class, regardless of how we got the E. Now, let me take another kick at this can. Suppose I have a positive test charge here, and it's being pushed by this sheet of charge. Now, remember, use your imagination. This green line is really a big old sheet that comes out towards you and goes into the wall forever. Okay, just keeps on going. Now, I'm going to break that sheet up into slats, like the gymnasium in your typical stake center. Okay, and so these are slats of charge that come out towards you. Is everyone seeing it? Quickly find out if your neighbor is seeing it. Okay. Now, if I look at the contribution due to this slat and this slat on that little test charge there, well, this slat is giving me a contribution away, and this contribution is giving me a contribution away. And I drew those arrows as red because we're actually looking at the force exerted on that positive test charge. Okay. Now, if instead, and when I add those together, most of it cancels. Okay, because this one is almost in the opposite direction of that one. And so when I add them together, I don't get very much push from that. But the push would be away, Now, if instead I looked at these 2 contributions, well, first of all, they're going to be bigger because they're closer. And they're also more in the same direction. They're not fighting each other as much. And so when I add them together, I get a huge push. And so what I'm going to suggest is that we define what I call a cone of influence that comes down at some angle, let's call it 45 degrees. I chose that arbitrarily. And that cone is going to contain all of the charge on the sheet that's pushing in the same direction. Okay? Almost the same direction. And so that charge is what's going to provide most of the push. Now, if I move that test charge up there, 2 things happen. One, it's further away from the charge. And we said that that goes as 1/r squared, twice as far away as 1/4 as strong. But the cone of influence also got bigger. And the area of that cone, of the intersection of that cone with my sheet, went up as the distance squared. Okay, I now have a lot more charge pushing in the right direction. And it turns out that those two effects cancel each other. The charge is pushing all together with a weaker, individually charges are working. Each charge on the sheet in this cone is pushing weaker on the test charge because it's further away, but I got more of them because I've got a bigger circle down there. See if your neighbor bought that one.
So it would be weaker, but there's more. Like stronger, but it's only two. Not like weaker, but it's like.
Guess it's not me.
Okay, let me take one more kick at the can. At Montana State University, one of our professors, Jack Drumheller, was an Air Force pilot, and he was ancient when I first started teaching there. And he shared with me the fact that during World War II, as there was fighting going on in the Pacific, if a pilot was hit and had to bail out of the plane, they prayed for rough weather. And that seemed counterintuitive to me. That seemed like a silly thing to pray for. But it turns out that when you jump out of your plane over the ocean, what you want to do is come down with your parachute, but before you land in the water, first of all, you don't want to land in the water with your parachute still above you, because it's going to land on top of you and pull you down under the water and drown you. And so what you want to do is when you're about 20 feet above the water, you want to unlatch your parachute, drop into the water, and swim as fast as you can away so that the parachute doesn't land on you. Now, what he told me was that if it's a calm day, if it's a beautiful, sunny, calm day, and there's no waves, the water just looks like a great big mirror, just flat. And it looks like it goes on forever. And it looks exactly the same if you're 20 feet above the water as when you're 100 feet above the water. But those aren't the same when it comes to letting go of your parachute, okay? And what they had were situations where the pilots would panic, that say, I don't want to get caught by this parachute, so that release themselves too soon and fall and break their legs and then be in real trouble. And so as long as the problem looks the same, the answer looks the same, okay? And that's what we're dealing with here. If the sheet goes out forever, I can't tell whether I'm this far above it or that far above it. That makes sense? We're believers, we're all believers now? Okay. Okay, let's practice with this problem here. This is in your homework 9, and the square plate with sides of 2 meters on each side. It lies flat on the floor, and the plate has a uniform total charge of 65 microcoulombs. Now, we want to know what the electric field is 1 centimeter from the surface of the plate. Part of that sentence is not necessary. What part is that? The 1 centimeter, okay? It could be 2 centimeters, 3 centimeters. And well, how close is close enough, Greg? Well, if that sheet of charge is 2 meters on a side okay, I want to be far enough away from the edges that the distance above the sheet is small compared to the distance to the edge. I want to be in the middle of the desert, so to speak. That makes sense? And then it doesn't matter whether you're really close or just sort of close. Now, in B, we ask what mass of a particle charged to 1 nanocoulomb would float 1 centimeter above the plate. And lastly, we ask if we took that particle and moved it up 2 centimeters from the plate and let go of it, would it move up, would it move down, or would it stay where we put it? Okay, so let's solve part A together here. And the key is that equation that we just gave you. And here I've got to apologize. Where did you get that equation? Okay. That equation comes from something called Gauss's law. It is the most beautiful physical law in the universe after Newton's third law. You know how I feel about Newton's third law, right? I feel almost as reverent towards Gauss's law. And I tried, I really did try to teach Gauss's law from the ground up when I started teaching some 40 years ago. Now, every semester I found that students were having a hard time with it. And so I'd spend more and more time on Gauss's law. And what I found was the more time I spent on it, didn't help. And so finally I just said, you know, I got other things I need to teach. And so Gauss's law is just something that it's never on the MCAT. And so it's not really something that I want to spend half of the semester on. So if you use Gauss's law and symmetry, you get that formula right there. But I'm giving it to you as just a gift. Okay? Now, remember, the first thing we need to do to find the electric field is to find the sigma. How thick did we spread that charge? Well, if I take the total charge, that's my 65 microcoulombs, and I divide by the area, it's 2 meters by 2 meters, or 4 meters squared, I get this value here, approximately. It's 16.25. We'll call it 16. Okay? Now, that just gives me the sigma. I want the electric field, so I have to divide it by 2, and I divide it by that constant that will be on the front page of your exam, 8.85 times 10 to the minus 12. And what I get is this value here, 9.2 times 10 to the 5th newtons for each coulomb. Okay? Well, that seems like a huge, huge electric field. And remember, electric fields tend to be really, really large, because an electric field is how much force I would have if I put 1 whole coulomb there. Well, I didn't put 1 whole coulomb there. I put a nanocoulomb, 10 to the minus 9 coulombs there. And so the actual force is going to be much smaller than that. If I look at a free body diagram, I've got weight down, and I've got this electric force up, the repulsion between that little charge and the plate. And that force by the plate on the particle is just going to be the charge of the particle, that's my Captain Kirk, times the electric field. This is what I'm scaling the electric field by. This is how much force I would have on 1 coulomb. I've only got this many coulombs, and so that tells me how much total force I have. This is the price of 1 gallon of gas. I only want this much gas, very little. Give me an eyedropper full, okay? And that gives me the total force. When I multiply that together, I get 9.2 times 10 to the minus 4 newtons, a small force. Now, if I want this thing to just hover, just float there, I want the weight of that to also be 9.2 times 10 to the minus 4, so that it has a net force of 0. Remember, what we were asked for in part B was not the weight, but the mass of that particle. What mass of the particle would I need so that it would just hover there, float there? And that weight is the mass I'm looking for times g. If we take g to be 10 on that mythical planet, then that's going to give me a mass of 9.2 times 10 to the minus 5 kilograms. Check that your neighbor could solve this if this were on an exam, because this is an old exam problem. This is an old exam problem.
I say.
Okay. Yes, where, okay. Oh, because it's not.
Okay. And I've already given away the answer to part C. If we move that particle up from 1 centimeter from the plate to 2 centimeters from the plate, the electric field doesn't change. That means the force doesn't change. That means that this particle is still going to hover there. And if I let it go, it's just going to stay put. Yes, sir. If you move it up a meter, you have violated the infinite plate approximation in that now the distance from the plate is exactly the same as the distance to the edge. You've gone beyond where it works. Good question. Good question. Okay. Now, a single charged plate doesn't happen as often as what we call the two parallel plates. A two parallel plate situation comes up over and over again whenever we deal with capacitors. And because these are so easy to charge up, we saw the two plate example when I had that bouncing ping pong ball. And the way we charged up those plates was that I stole electrons from the bottom plate and I moved them over to the top plate. So we're going to find that we can either do that with a Van de Graaff generator or we can do it with a car battery. If we take a car battery and just hook one plate to the negative terminal and one to the positive terminal, we're going to steal electrons from one plate and give them to the other plate. And so what we end up with is two plates that have the same size of the charge, same magnitude of the charge, but one's charged positively and one's charged negatively. Okay. For every electron that I steal from the one plate, I leave a naked proton behind. And so I have exactly the same amount of charge on the negative plate as the positive plate. Now, the positive plate's going to have parallel field lines that are going away from the positive in both directions. The negative plate is going to have parallel field lines that go towards the negative from both directions. But when I add those two together, when I use superposition, what I end up with is the combined electric field of both. Okay, well, let's look at what that looks like. I've got this positive sheet. Remember, it comes out forever. The purple one's a negative sheet. It comes out forever. If I look anywhere between the plates, right here, I get a contribution that is away from the positive and a contribution that is towards the negative. And I made those contributions the same size. Tell your neighbor why. Why? Why?
Fields. Us.
Okay. What you should have just told your neighbor is, I got the same size sigma and distance don't matter. It doesn't matter that I'm further away from the negative plate than the positive plate. Distance don't matter. Okay. And so these are the same size. And that gives me my total electric field. If I had chosen a point closer to the negative plate, I would still have a contribution away from the positive towards the negative. Again, those are exactly the same size as each other. and they're exactly the same size as they were down here. And so I get the same E net. And no matter where I choose between the plates, I get exactly the same electric field. And that makes this a very useful device. There are a lot of experiments you want to do where you want to control the electric field. If you have two great big charged plates, one positive and one negative, the electric field is going to be exactly the same anywhere inside those plates. And that allows you to perform a controlled experiment. Okay? Now, what if I look outside the plates? Well, now I have a contribution away from the positive, but now away from the positive is down. I have another contribution towards the negative, and it's still up. And these two are the same size as each other, because again, distance don't matter. Okay? And so those are going to cancel out and give me 0. And that's another advantage of this parallel plate situation. When you're doing an experiment, you want an electric field in there where you're doing the experiment. You don't want an electric field in the rest of your lab where it would mess things up. And so this parallel plate situation is going to give you what you need. Okay? And if I looked up here, it would also be 0. So how big is that electric field? Well, let's use superposition. Okay? It's made up of 2 parts. And I know how big each part is. Okay? Remember, it was sigma over 2 epsilon naught. But I'm going to write it as 1/2 times sigma over epsilon naught. That's not going to offend anybody, is it? You're going to sleep at night if I do that? Just take the 1/2 over a little bit to the left, baby step. The electric field due to the negative plate is exactly the same size. Now I'm gonna make up some terminology here. I'm gonna call this combination sigma over epsilon naught. I'm gonna call that apple pie. Okay? And I have a half an apple pie, and I have a half an apple pie, and I'm gonna add those together. What have I got? You got a whole apple pie. Got a whole apple pie. Okay? And this is the third equation that we will have on the front page of your exam. We have Coulomb's law when your source charge is a point. We have sigma over 2 epsilon when you have a single sheet. And we have sigma over 1 epsilon if we have 2 sheets. But you got to be careful. The 2 sheets have to be equal and opposite in charge. Now you're going to get a homework problem where you've got 2 sheets. And some of you will run to that formula. But one of those sheets has twice as much charge as the other. And you're going to be in trouble. Okay? This one only applies when the 2 sheets are equal and opposite in charge. Talk to your neighbor. See if your neighbor understood what that meant.
If that's.
I know.
Two halves.
Okay.
Alcoholic.
My E field is 0 up there, and it's 0 down here, and it's this big in between. And what would that look like? Well, if I want to represent a region here where there's no electric field, and a region up here where there's no electric field, I would put no field lines. And in here, I want to represent an electric field that is everywhere uniform, the same value. And so I would use field lines that are parallel to each other, because that tells me that the electric field here is the same strength as the electric field there, is same as the electric field there, everywhere between the plates. So that's what your field lines look like between 2 plates, one positive, one negative, equal surface charge. And that we're going to see a lot. That we're going to see a lot in the homework and on the exam. Now, to summarize this 2-step dance, once again, you've seen this again. The first step is that a source charge creates an electric field, changes the room. Okay, but now, unlike before, we have three ways that it can change the rule. If it's a point source, I use Coulomb's law, where K is this value. If I have one sheet of charge, I use this formula, sigma over 2 epsilon naught. If I have two sheets that are equal and opposite, I use this formula, sigma over 1 epsilon naught, where this is epsilon naught. Okay? And these three formulas will be on the front page of your exam. The equation sheet for that next exam is already up at the MAC site under the sample exam location. I'm not finished with this slide yet. I haven't talked about step 2. Step 2 is you use that electric field to find what you really care about. The force on this test charge, this Captain Kirk. Okay, and again, that's a vector equation. So if your test charge is positive, the force and the electric field are in the same direction. If your test charge is negative, the force and the electric field are in opposite directions. And that's it. That's all there is. If there were more, they would pay me more. See if your neighbor understands all there is. Everything. The whole shebang.
No freaking breaking the sound barrier crap. None of that.
Are you on the bus? Who has to make a whole?
Left.
Unless you have a negative.
Like-
No, I'm fine.
Okay.
Okay.
I'm going to say it one more time. If your charge is in a point, you use this formula to find the electric field. If you have one sheet, you use this formula. If you have two sheets equal and opposite, you use this formula. But however you found the electric field, you can plug it right in there. And that's why we do this in a two-step dance instead of just doing it all together. Okay, is because we have different ways of finding the electric field depending on the charge. Yes.
Sheets, but they're not.
Ah, yes, that's a wonderful question. If they're not equal, you have to use this formula twice. You have to use superposition and say, oh, with one sheet, I got a contribution up that's this big. For the other sheet, I get a contribution down that's twice that big. And then you add your answers together. Okay. I made a joke back in Montana. I said, when you get a problem that you can't handle with one of these equations, you stand up and you say, hello, my name's Greg Francis, and I have a problem that I can't solve. And, you know, like they say at the beginning of an Alcoholics Anonymous meeting, and the students laughed. But then it came back to me later that at the local, I had a lot of students. And so at the local Alcoholics Anonymous meetings, the big joke was to stand up and say, hi, I'm Greg Francis, and I have a problem that I can't. So we're not going to have that problem here. Okay. So moving right along. This is the type of multiple choice question you could expect on the exam. Points A and B are located as shown between two large means way large, okay? Large enough that you can use those equations. Large uniformly charged parallel plates. One of them's positive and one of them's negative. Which of the following correctly describes what happens to the electric fields at A and B if the plate on the right, the negative one, is taken away, is removed, magically disappears? A, the field at A drops more than the field at B. B, the field at B drops more than the field at A. C, both fields remain the same. D, both fields drop by the same amount. With your clicker, people.
It would have right. Yeah.
Take one away, then we would just be using this equation. And since.
Okay, get your clicker points.
I like it.
Last call. Okay, good. The field drops by the same amount. Good. And that same amount would be by a factor of 2, right? Okay. Whoops. Okay, let's talk about conductors. Not that kind of conductor. Okay, not that kind of conductor. Let's look at one of your homework problems. 9-3. A point charge is fixed in place in front of a large plastic sheet that contains the uniform surface charge. When an electron is placed halfway between the point charge and the sheet, it feels no electric field, none whatsoever. Okay. Now, we want to know in part B, what's the electric field do to the point charge alone? Well, that point charge is positive, and you notice that I made a mistake there by making it purple. Yeah, that's on me. Okay, it should be green. Okay, but my electric field is going to be away. I just needed different colors. Okay. Now, the second, the part C asks, what's the surface charge density on the sheet? Remember, if I put an electron at that point, it feels absolutely no electric field. And so that means that the electric field there has to be in the opposite direction. Now, I'm not going to work out the size of those fields or the size of that surface charge because it's going to be different for every one of you. How would you find the purple arrow? What formula would you use to find the purple arrow? Shout it out. Coulomb's law. Coulomb's law, because you've got a point source. How would you find the sigma? Well, you'd use the formula for a single sheet of charge. And you know how big this electric field is. You could find out how big the sigma is that causes it. Okay? Now, things in this problem now get a little hinky because we add a neutral metal block. Okay? And in a metal block, a conductor, the charges are free to move. The electrons are free to move, not the protons. The protons are stuck in the lattice work as part of the nucleus of the atoms, okay? But the electrons can slosh to where they're happy. And that's what makes a conductor special. And so in this case, I know that I've got a big old positive sheet there, and I've got a great big old positive charge there. And so that means all of this positive charge is going to attract my electrons to the left. Is that right? And that's going to leave naked protons over here. Now, here's why I bring this up. These guys, this sheet here, we were told is a large plastic sheet, meaning it goes on beyond the picture. Huge. And that means the distance away from it doesn't matter. Doesn't matter. This guy here is a little block of metal. And so even though I've got a sheet of charge here, it's a concentrated sheet of charge. And so distance does matter. And so when I look at the electric field contribution due to these electrons, that's going to be towards the negative electrons. And when I look at the electric field over here, due to those positive charges, that's going to be away from the positive charges. But these positive charges are further away than the negative charges. So this green arrow is shorter than this dark blue arrow. Does that make sense? Even though it's a sheet, it's not a large sheet. And so distance matters. And that's why when we had charge separation in the tin can, we got an attraction. Okay. So the net electric field, if I add up all of those arrows, is going to be what direction? Tell your neighbor.
Right.
Okay. I hope you said to the right. Wait a minute, Greg. Wait a minute. You put an electron at the X. Yeah, I did. So the electric field doesn't care what's at the X. It could be an elephant, could be a rhino, it could be a mailbox. The electric field has the waffle words, if I reach into my pocket, and if I pull out +1 Coulomb, and if I put it at that X, what would it feel? Now the force on that electron that I put at the X, that I really put on the X, the force on it would be opposite the electric field or to the left. Okay. But you have to keep straight when you're talking about the electric field and when you're talking about the electric force. The electric force is the actual push on the actual electron that I actually put at that X. The electric field has the waffle words. It's using your imagination. Check that your neighbor is going to be able to do this homework when he gets to it. He or she gets to it. Okay. Would someone back there ask a question so that I can see whether this is going to save me from running back every time? Someone back in the back asked me a question.
Is Captain Kirk your favorite Star Trek character?
No. That would be Mr. Spock. Okay. And it works. Thank you very much. I appreciate that. Life is, I tried over and over again to charge that to the university. It just never would let me. So I had to pay real money for that. Okay. Let's practice a little bit. Suppose I have two infinite insulating sheets with fixed charge. They have the same amount of charge. One's coming out horizontally, one's coming out vertically, splitting the class in half. And if I go right along that symmetry axis and ask you which of those directions would be the direction of the electric field, with your clicker, go ahead and choose.
I think it would be well positive now.
I feel like a trick question.
Let's do something free.
Okay, that's the easiest question you're going to get all semester, people. Okay, last call. Get your vote in. Good. We almost got a perfect score, but 10 people are keeping us from going to Disney World. Thank you. Okay. We use symmetry to answer that question. And remember, symmetry is just one day I'll be sitting at that desk and you can't tell the difference between the left one and the right one. But what if I look at point 2? Okay, what if I look down here at point 2 and ask you the same question? Which of those directions would be the direction of the electric field there? And you could vote now.
Heck no.
If you'll agree that it's not, it's just about This is like.
Okay, last call.
Yeah, but it's distance, the distance.
Good. The answer is B. Okay,
That comes.
we use superposition here. If I look at the contribution due to the horizontal sheet, it's away and it's a certain size. And if I look at the contribution due to the vertical sheet, it's away and distance doesn't matter. So that means it's got to be the same size as what I started with from the horizontal sheet. And so it's going to go off at 45 degrees. Okay? And that's because the distance doesn't matter. Now, let's talk about conductors in the last little bit that we have here. That purple slab represents a hunk of a plate of metal of a conductor that's coming out towards you in a big way. It goes on for a long way. And if I take a big bucket full of electrons and dump it on that metal slab, okay, so I've got a whole bunch of extra electrons, I'm going to argue that they're not going to want to be close to each other. And they can swim wherever they're comfortable. And so they're going to swim as far away as possible from each other. And half of them are going to be on the left and half are going to be on the right, because I can't tell the left from the right. So there's no reason to argue that one would get more than the other. Okay? Now, if I look at the electric field anywhere inside that slab of metal, I see two contributions. I've got a slab over there that's half of the total sigma. I have a sigma over there that's half of the total sigma. If I look at any place inside the conductor, I have a contribution that's going to be towards this sheet. And the size of that is going to be my sigma left over 2 epsilon naught. And since sigma left is half of the total sigma, that would be that big. I also have a contribution due to this negative sheet that's the same size, but the opposite direction. And so those two contributions give me 0. Now, folks, that's the big message about conductors, is that any excess charge, any extra electrons will swim to their happy place until there is 0 electric field inside the metal. And you have to be patient for that to happen. It's going to take 10 to the minus 16 seconds. Blink as fast as you can. That was way slow compared to 10 to the minus 16 seconds, okay? So if there's excess charge that goes onto a piece of metal, almost instantly, those electrons will already be moved to their happy place. So the electric field is 0. Now, I used a very, very simple geometry here to make that argument. But it turns out it's true for any conductor in any shape. It can be a general on a horse made out of copper, okay? Anywhere inside the general or inside the copper horse, the electric field is going to be 0. If it weren't 0, you'd still be pushing electrons to their happy place. And it doesn't take very long for the electrons to already get to their happy place. And when they get there, there's no electric field pushing them anymore, okay? Now, we call this electromagnetic shielding. Now, we had a room in Montana where students would build what they called CubeSats, little tiny cubicle satellites that were sent up in the space shuttle and then released with experiments inside them. And the last thing they would do when they were finished with their CubeSat was cover it with aluminum foil. And indeed, you go to NASA Space Center Seems like everything's covered in aluminum foil. And that's because you want to shield what's inside your container from electric fields outside your container. The electric field's got to be zero everywhere inside that, that metal. Now, there's another side to this, and that is, and this becomes important, the electrons are free to move along the surface of your satellite as well. And if there was a component of your electric field that was tangent to that surface, it would still be pushing electrons. But if you wait 10 to the minus 16 seconds, they're not moving. There's nothing pushing them. And that means that when you have a metal surface, the electric field has to come into it at 90 degrees. At 90 degrees. It has to be. It has to be. Now, I had some demos here, but I don't have time to do them. And so I will do them when we meet again. And we're going to meet again, not Tuesday, because Tuesday is a Monday instruction day. Our next meeting will be Thursday.
Oh, yeah. Monday's a holiday. Tuesday is Monday.
Monday.
You have that.
I think I feel like it's coming here.
It's okay, I'm in bio.